Good morning. Today's topic, multiple reactions. It's continuation of multiple reactions. Multiple reactions, okay? So before going to actual topic, I'll be defining two new terms today. What are those new terms? It is instantaneous yield and overall yield, okay? So what is this instantaneous yield? Instantaneous yield and overall yield. Overall yield. Okay, so this instantaneous yield, it is denoted by phi and this is denoted by psi. Okay, and this is moles of the desired product formed. It's defined as moles of desired product formed by moles of reactant taken initially. Okay, so this can be written as CRF by CA naught. Suppose I take the reaction, A gives R. To take the reaction, I can write that as moles of desired product by moles of reactant taken initially CA naught. So this is, the numerator remains the same. It's moles of same desired product formed by moles of reacted okay, moles of key reactant, and this will be CRF by CA naught minus CA. Okay, CA naught minus, if I call this final, let me call that as also fine. That is what I used in the notes. Let me continue with that. Okay, CRF by CA naught minus CA. Okay, now selecting the pattern for a better yield. Selecting the pattern for a better yield is the next topic. I'll write this. Selecting the pattern for better yield. Okay. So for this, now let me consider one parallel reaction in which A gives R and A gives S. Okay. So A gives R and A gives S. Let me call R as a desired product. Okay. So this is the desired product, but A is simultaneously parallelly giving S also. Okay. So now R can be written as K1 CA, R to the power of N1. RS can be written as K2 CA power N2. So now what I'll write? I'll try to write RR by RS, which is equal to K1 by K2 CA power N1 minus N2. Okay. So I need this. I mean, I have got this. From here, we will keep discussing different cases. Okay. Yeah. So this ratio has to be maximum for better yield. Ratio has to be maximum for better yield. Okay. So now to maintain this ratio maximum, how do we maintain the maximum ratio? Okay. So all this is a topic what we will be studying now. Okay. See, to get the better, one important thing we need to note here. Can I change the order of the reaction? No, I cannot change the order of the reaction. But in spite of, without changing the order of the reaction, how do I increase the yield? They are orders. I can't change them. They are the nature for the reactions. From the reaction, we have got that. We cannot really change it. In spite of that, if I want to have a better yield, what do we do is a next topic which we'll be discussing. Okay. So here, this equation is sufficient for me to continue. So let me rub this. So let us go with by case. So here, case one, n1 greater than n2. You see, case one is n1 greater than n2. Okay. If see n1 is greater than n2 means see this is for n1 and this is for n2. Okay. If this path is greater than this, obviously increasing in A will give me more R. You getting that? See, if n1 is greater means what? This path will be greater. K1 will be greater than K2. If K1 is greater than K2 and N1 is greater than N2, obviously this will give me more, the ratio will be higher. Okay, and if this concentration is higher and higher, if A is higher, obviously I get more R. That is the thing. Okay. What as a conclusion is, which means if N1 is greater than N2, ratio RR by RS is maximum. Okay. K1 will be greater than K2 also. Okay. So now this will be max at what? At higher concentration of A. If I increase the concentration of A, this ratio also increases. That is the meaning. If I am increasing the concentration of A, this path is favored. Anyway, if I increase this also increases. That is the meaning. So this path is favored. So this will be achieved at high concentration of A. Now, how do I maintain this high concentration of A? So PFRs are used to maintain higher concentrations. PFR and even the batch reactor can be used. So conclusion is, therefore, PFR or batch reactor is used to maintain high concentration of A. High concentration of A. This is first case, case 1. Next, case 2. Case 2 is what? N1 is lesser than N2. Okay. So what does that actually mean? So N2 is greater than N1. That is the meaning. See, N2 is greater than N1 means what? This path is higher than this path. Okay. So if this path is higher, if I take more concentration of A, what happens? S is getting more S is getting formed. If more S is getting formed, my desired product form will be lesser. Correct. So if I take higher concentration of A, more S is formed and less R is formed. So I have to minimize the concentration. So what should I do now? Yeah, that is what is the next thing. So if I want to maintain lower concentration of A, I'll take A in a CSTR. That is the meaning. I should take. If I take this in a batch reactor, then this will be proceeding at a higher rate than this one, which is not the desired product. Okay. One second. Let me mute this. So yeah, let me explain that again. See, if N2 is greater, this reaction will be favored if higher concentration of A is taken. So I don't want to take higher concentration for A and favor this reaction. So what I do, I have to take lower concentration for A. So to get this lower concentration for A, what I do, I take A in a CSTR. That's the meaning. So A is taken in, A should be taken in CSTR, and A should be lower. A should be lower. If A is higher, more S will be formed. Okay, that is the meaning. Okay. Case 3. Case 3. Case 3 is a very bigger one. Let me rub this. Case 3 cannot be explained in terms of concentration directly. Case 3 is what? N1 is equal to N2. What do I actually mean by that? It doesn't mean zero order reaction. Both the reactions are of same order. That is the meaning. Okay? So if both the reactions are of same order, what do we write? RR by RS will be equal to K1 by K2 into, it is independent of concentration. So this is what we get. Okay. So now what does this indicate? This indicates this type of reactions wherein if this is both are of same order, they are not dependent on the concentration. They are not dependent. Whether the production of R or S is not dependent on initial the concentration of A. Then what else will affect the rate is the question. So to understand this, what else will affect the rate? No? Let us have a recap of the graph which I had shown you in my introduction class. That is Arrhenius plot. Okay? So what is this Arrhenius plot? Let me show the plot. Let me use the same notations and what I have used in the lecture notes. Okay, I have it here. I have taken as K1 is equal to K01 e to the power of minus E1 by RT. K2 is equal to K02 e to the power of minus E2 by RT. Okay. So yeah, both of them I'm taking at the same temperature. So what can I now write here? I can now write this as K01 by K02 e to the power of E2 minus E1 by RT. Okay, I can write this equation. Can you see? Yeah. Now what I do? Now I rub this actually. I don't need this. Okay. So to explain, I need more space. Let me rub this. What was the Arrhenius plot? Arrhenius plot is ln K versus 1 by T. And here I had clearly explained lower activation energy, slope will be lesser, lower E. Okay. If higher, for higher values of E, it is steeper. So this is higher activation energy. So these are the lines for lower activation energy and higher activation energy. Okay. So now this is what we are maintaining, right? K1 and K2. If anyway, I don't want to go with the equations. I'll explain with the graph. Okay. So now what I do at some point, let me take a line where I can get the ln K values for both. Okay. So if I take here, if I take this point, this will be what? This will be what? Ln K. Okay. Let me. If E1 is greater than E2, means this will be your E1, right? Now I'm showing this one. Okay. E1 greater than E2 means that is activation of energies of first reaction. If activation energy of first reaction is higher, then for first reaction, this is the nature. If the activation energy of second is lower, this will be nature for the lower activation energy. Okay. So now I can call this as ln K2 and this part as ln K1. Ln K1. Okay. So here what I have shown, if E1 is greater than E2. Okay. If E1 is greater than E2 here, what is happening with the increase in, see, 1 by T goes like this, but what happens to T? T will be increasing in this way. Okay. So if E1 is greater than, see, if this E1 is greater than E2, no, ln K1 will be, ln K1 by K2 will be higher. Correct? The ratio is higher. So the if E1 is E1, you can observe here only, ln K1 is higher, so this ratio will be higher. If because of this higher values, no, K1 by K2 will be higher. Okay, so RR by RS will be maximum. K1 by K2, no, this will be higher. Okay, so what does that indicate? Higher temperature favors the higher temperature will increase this ratio. See, as the temperature is increasing, the ratio goes on increasing. Ln K1 by ln K2 goes on increasing. So higher temperature will increase the ratio. Increase the ratio. Increase the ratio K1 by K2. K1 by K2, and thus increases what? R by RS. Thus increases the A. Okay. So the reactions are to be carried out at higher temperatures. If the activation of energy of this desired reaction is higher, if the activation energy of the desired reaction is higher, the reactions are to be carried out at higher temperatures. Okay, I'll conclude here. Reactions to be carried out at high temperatures. High temperatures. Okay. Okay, note of that. If we come to the next case. Next case, this also I don't need anyway. Have it there. Next case is, second case, if E2 is greater than E1. That is, activation of second reaction is greater than the first reaction. If the activation of energy of second reaction will be higher, no, this will become E2 now. This will become E2. Correct? Activation of higher activation energy gives me steeper slope. So steeper slope line should give me E2 now. Are you getting that? Higher activation energy, steeper slope, and steeper slope here will be given by E2. E2 gives me the, E2 is a higher activation energy. So for the steeper slope line, I'll denote that as E2. That's it, okay? And this will be E1 now. This will be E1. So this will be ln K1 and this will be ln K2. Okay. So if I increase the temperature now, what happens to the ratio? It decreases. Correct? If I increase the temperature now, see here, if I increase this now, ln K1 by K2, see, ln K1 by K2 will be lesser. K1 is lesser than K2. Denominator higher value. So this ratio decreases. RR by RS is equal to K1 by K2 decreases if T increases. If T increases, okay, if T increases, now if actually T, the actual meaning is if I increase T for this path will be favored. This path will be favored, but this is not my desired path. Got it? If I increase the temperature, if activation of energy of second reaction is greater than first reaction, then if I increase the temperature, this path will be favored. If this path is favored, the desired path will be lesser. Okay, the desired path will be lesser. So this ratio, the ratio decreases if T increases. Therefore, with that also, if I want to maintain if I want to maintain the higher concentration of product, I should carry out the experiments at lower temperature. Therefore, the reactions are to be carried out. Therefore, in these cases, reactions are to be carried out at lower temperature to get better yield of R. To get better yield of R. Okay. So if higher temperature is there, this will have higher activation energy. This part will be favored, which is not required. Okay. So yeah, this is the conclusion. What else I have concluded? Let me check. And for these cases, no, for if T increases, undesired reaction favors. What is that undesired reaction? This part. If T increases, undesired reaction favors. Okay. Yes. Hope it's clear. Yeah. Now. Yeah, I have covered this. Okay. Next. Fourth case. So if N1 is equal to N2, no, then the reactions will be, you have to check the temperature. If the orders are same for both the reactions, then then it depends on the temperature. So we have to check at what temperature the reactions are to be carried out. Okay. Next one is the last one on which the reaction depends. This part, R path or K1 path or K2 path is the catalyst. See, but catalysts are highly selective. The selectivity of catalyst is very, very important. Okay. So if you select a catalyst which catalyzes undesirable reactions, then no use of using that catalyst. So the selected catalyst should catalyze only the desired reaction. The selected catalyst should catalyze only the desired reaction. So other key factor is selectivity. Okay. Case 4, it is selectivity. So all the cases are being explained now. If N1 is greater than N2 or N2 is greater than N1 or if N1 is equal to N2. So all the cases are being explained now. So let me summarize. Summary is concentration of reactant is the key for proper control of reaction. We can conclude that by understanding N1 greater than N2 or N2 greater than N1, we can conclude what is that concentration is the key factor for the proper control of reaction. Okay. Second point, higher concentration favors higher order. Higher concentrations, this is what we had right? N1 greater than N2. Higher concentrations favors higher order. Higher order, okay. And how do you maintain the high concentration? Higher concentration for the reactant can be maintained using a plug flow reactor or a batch reactor, or a batch reactor can be used. Okay, so CSTRs will maintain lower concentrations. Next, next conclusion is for reactions with higher activation energy. For reactions with high activation energy, increase in T favors the reaction. Increase in T favors the reaction. So for reactions with lower activation energy, for reactions with low EA, low activation energy, lower temperature favors the reaction. So these are the conclusions. Hope I concluded everything. So these are the conclusions which you should note. Okay. Next is how to maintain these conditions. How to maintain high concentration. For which reactant I can if the concentration is suppose I have two reactants A and B. So how do I maintain B high or A low or A high or B high? That is what is the next topic. Okay? Yes. This is all selecting the patterns for better yield. Okay. Yeah. In this, we will be studying under different headings. We'll be studying this under different headings. First one is batch reactors. Batch reactors. Okay. So in batch, first case, CA and CB both high. Case 1, CA and CB both high. Second, CA and CB, here only I'll write both low. Okay. If I am going with the batch reactors, I'm not going with the flow reactors. This is first with the batch reactors. Then we will study the flow reactors. Okay. So if I'm going with the batch reactors, if I want to have a batch reactor, CA and CB are taken at once into the reactor, and A and B, and A and B at once into the reactor. Okay. If CS and CP both low in the batch reactor, then add A and B both drop price. Both drop price. Okay, into the batch reactor. What is the next case? What is the next case I have done? Let me check. The next case is CA high, CB low. This is case 1, case 2, 3. CA high, CB low. Or fourth case will be CA low, CB high. Okay. So if I want to maintain high CB, then we will go with semi-batch reactors. What are semi-batch reactors? Semi-batch reactors is one will be taken in batch mode and the other one will be taken in continuous mode. Okay. So for that, if I need high CA, high CA, then I'll take that in a batch mode. See, anywhere you need higher concentration, it should be either taken in plug flow mode or batch mode. So which is higher? A is high. So A will be taken in the batch, and B will be added. B will be added here. Okay. Add B slowly. So this is a semi-batch reactor. Semi-batch reactor. Take A. Take A in batch reactor. Batch reactor. Add CB slowly. Add CB slowly. Okay. Now you should be able to understand it. If CB has to be high, CB should be taken in batch mode. Okay. And A will be taken in. This is also semi-batch. Okay. The next one is flow reactors. Pin up this. Let's pin up this. So you have done 1, 2, 3, 4. Flow reactors. Flow reactors. Okay. So in this first one, CA and CB high. Case 1, CA and CB both high. Okay. So if I want high, then both should be in plug flow mode. So what I do, I'll show you a plug flow reactor. A and B both in pair form. Okay. Or else the other way is connecting n CSTRs in series. At the end of my video, I'll show you how n CSTRs will be equal to 1 pair form. So A and B. Sorry, 1 second. I can't pass them together because both should be higher, no? Okay. Yeah. So this is a CSTRs in a series with with side stream B. With side stream B. A will be taken here in all the reactants. A will be taken. Okay, and side stream of B will be given. So these are CSTRs in series. CSTRs in series. Okay, so tau 1 PFR is equal to n CSTRs in series. N CSTRs in series. Tau for NP for PFR is equal to tau for n CSTRs in series. At the end of my video, I'll show you because this is again it will be recap of multiple reactors. Okay. Next one is what is it? CACB both low. Second case, CA and CB both low. Both low means I can easily use CSTRs. Okay. So take a CSTR, send CA, CB, draw the products. CA, CB. Okay, both low. The other way of achieving this is a recycle reactor. Of course, we will not be studying recycle reactors. It is not there for your syllabus. But a very interesting topic. Recycle reactors are a very interesting topic. Okay. And how have I shown? Okay. This is A. This is B. Okay. See, CA and CB, when they mix together, there is neither high concentration of A or low concentration of A. Both will get lowered. Okay. So this is recycle reactor. This is one way of getting both CA and CP both low. Okay.